Hello, and welcome to the third and final installment in this series of lectures, where we're going to introduce a few undecidable problems. So what did we do in the last lecture? We mentioned the Church-Turing thesis, and it occurs to me I didn't actually give you one of the punchlines. Namely, Church and Turing each did succeed in answering Hilbert's Entscheidungsproblem. In other words, they showed that there will never be an algorithm to take as input a formula in first order logic and say, is this a valid formula or not? On the other hand, that set, the set of valid formulae, is recursively enumerable. It is Turing acceptable. Why is that? Because there is an enumeration of all of the theorems. It turns out to be the case that anything that's valid has a proof, and you can just enumerate proofs, enumerate all the one-letter proofs, all the two-letter proofs, all the three-letter proofs, and each time you find a proof of a theorem, you can enumerate the thing that was proved, and so that shows that the set of valid things is enumerable. What Church and Turing showed was that it is undecidable. Let's give some other examples of undecidable problems. And in order to motivate that, the first thing we're going to do is talk about an important notion called the universal Turing machine. So what goes on with the universal Turing machine? What makes it universal? Well, remember, we made the argument that no matter what programming language you're working in, anything you can do in that programming language, you can also do with a Turing machine. And it's certainly the case that in any programming language, you can write a simulator. What is that? It's a program, here I'm calling it sim, that takes as input the encoding of a program and some string X, and you run the program on X. So I'm using these angled brackets the same way that the textbook does to indicate that the bit string that represents a program is this P with angled brackets about it, and that's differs only in a very slight way from the program itself or the function computed by that program. But it's it's a difference that's being highlighted in the notation that way. So since if you can do that in your favorite programming language, well, then you can also do it with Turing machines. And that machine is called the universal Turing machine. What does it do? It takes as input an encoding of a machine M and a string X, and it outputs whatever M outputs on input X if that computation halts. And otherwise, we just say it's undefined, which you can think of as meaning the computation doesn't halt. Now, this machine, like any other machine, has some language that it accepts, and we call that the language of that machine, L of U. And that has a very special name. We call it A sub Tm, which is those pairs M of X, M and X, such that W is accepted by machine M. Okay, so A sub Tm is certainly going to be one of the languages that we'll be working with. And the very fact that there is a simulator is certainly a crucial and important fact about Turing machines. Now let's move on to the question about what are some examples of things that are undecidable. The first thing that we should note before we give any specific examples is that there are only countably many programs because what is a program? A program is just something you can write down. So it's an element of sigma star, and sigma star is a countable set. And so this is also certainly true for Turing machines. There are only countably many Turing machines, but there are uncountably many subsets of the natural numbers or of 0, 1 star. In other words, there are uncountably many languages. So in some sense, hardly anything is computable. There are just way more languages, way more functions than there are programs. So hardly anything is computable, but that's not nearly so interesting as to know some specific examples. And one famous example, one important example to know about is the halting problem. There are different versions of the halting problem. We're going to define it as being the set of all machines M and input X, such that M on input X halts. Different texts would define this as being the set of all those machines M that halt on their own input, on their own encoding. And I don't want people to freak out when they always encounter these examples about programs being run on their own code, because this is something that happens all the time. There are a lot of programs that take other programs as input. Think about compilers, for example. If you've got a Java compiler, you can write that in Java, and you can use that compiler on its own code to compile its code. So there's nothing really weird about having programs run on their own input. It happens all the time. And we will certainly be seeing other examples, which maybe do look a little bit weird later in this lecture. So I will claim that the halting problem, let's just call it H, is recursively enumerable. It's Turing acceptable. Why is that? Well, you take as input M and X, you run using our universal Turing machine, you run M on input X, and if that computation ever halts, then you go to an accepting state, and otherwise, of course, if it doesn't halt, there's nothing to worry about. You will never halt, and in particular, you will never accept. So it's definitely Turing acceptable, but it's not decidable, which means that H complement is co-RE and not RE. Okay, so almost all of the examples that we will be giving, well, in fact, every example that we'll be giving in this lecture is going to be something that is computably enumerable and not decidable. Therefore, its complement is co-RE and not CE. Okay, so how do we prove this? This is a theorem. It'll be a proof by contradiction. Assume otherwise. So in particular, assume that halt is some subroutine, some program that decides H. Well, then consider the following program, which I'm going to call bad. Bad takes input the encoding of a machine, M, and what does it do? It runs program halt. So if halt, that subroutine, that magic subroutine on input M, M says yes, then this program will loop forever. And otherwise, it will halt. And let's say halt and accept, whatever. Okay, so this is a program. And like any program, it can be represented by a bit string. And I'm going to call this bit string B, the encoding for that program B. So the question now is, does program B halt when it's given its own code as input? Remember, it's a program. You can run it on any kind of input, including its own program. And I'm using this down arrow to indicate halt. So this is the question. And note that if the answer were yes, well, then what's this program do? It goes, remember, we're running B, which is this program, on its own code. And if it does halt, its program by definition is going to output yes, which means that this program B will loop forever, which means that if the answer is yes, then the answer is no. So that's impossible. So that means that the answer is no, but if the answer is no, you go down to the otherwise or the else part of this statement and you halt. So if the answer is no, then the answer is yes. That's a contradiction. So in other words, this program is nonsense. It can't possibly exist, but it does exist assuming that halt is a routine. In other words, if there's a Turing machine, if there is some decidable algorithm that halts and actually decides the language H. So that means it's not decidable. So good enough. What's something else that we can now say is not decidable? Let's look at A sub Tm. We're going to claim that this is recursively enumerable, computably enumerable, and not decidable, which means that its complement A sub Tm is co-RE and not RE. So we're going to assume that A sub Tm let's call it accept, is some subroutine that decides A sub Tm. Now, what does that program look like? Again, we're going to call it bad on input M if, now we're going to call accept on this input MM is yes, then we will reject, we halt and reject. Else we will accept. So if I'm given a subroutine that always halts and returns yes or no, then this routine bad is certainly something that we can write. And now let's call this piece of code B. And the question is now, is the encoding of B in the language accepted by that machine B? Well, what do you think? If it is, then our subroutine AX is going to say, yes, this program that we're looking at, B, accepts if we run it on input B, and in that case we reject. So if it is accepted, it's rejected, so that can't happen. Therefore, the only possibility is that it's not accepted, which means that this is going to return no, which means we go down here to the otherwise, and we accept. So if it's not accepted, then it's accepted. Again, we get exactly the same contradiction. So there you have it. Yet another example of something that is Turing acceptable and not decidable. So remember this handy dandy diagram where we have the computably enumerable sets and the co-computably enumerable sets. We've shown that the halting problem and A sub T M, and actually also, don't have room to write it here, but the Entscheidungsproblem, the set of valid formulae, maybe I'll just call that V, the set of first order statements that are valid. Those are all here, whereas their complements are all over here. And later on in a subsequent lecture, you will learn that in some sense, these are actually all the same problem. In other words, given an instance of one, you can transform it into an instance of the other, and all these problems are what is known as complete. You'll learn an important vocabulary word about completeness, and that will happen in a later lecture. So let's just recap where we have been in the last few lectures. We've started with what you learned about in the previous lecture about Turing machines, and note that there's sort of a robustness to the definition of Turing machines, that just about anything that you would like to tweak the Turing machine model to get will give you something that's equivalent to Turing machines. And basically, it's also going to give you something that's equivalent to programs. And certainly we're familiar with the notion that there are tons of different programs out there, programming languages, and they're all equivalent. Turing machines are really, in some sense, just another sort of inconvenient programming language, but they have the advantage that they're very simple to work with. We learned about the Church Turing thesis, and that the real meat of the Church Turing thesis is just this statement, that no matter what notion of programs you come up with, it's going to be something you can implement on a Turing machine. And an important corollary then is that if something is not computable by a Turing machine, in particular if it's not decidable or if it's not even Turing acceptable, then it's not going to be decidable or acceptable on anything else that you come up with that looks like it ought to be a notion of computation that you can actually implement. This was something that will never be proven, but it's something that is pretty widely accepted in the community at this point, although I must say not universally accepted. We've also given some examples of undecidable problems, and central to this universal Turing machine, which just relies on the very basic notion that you can build a simulator for Turing machines or for any other programming languages using a Turing machine. And this gives us examples of undecidable problems like the halting problem and A sub Tm, and in some sense also underlies the fact that the set of valid formulae is not decidable, and even sort of complicated proofs about other natural problems that people cared about and still care about, like Diophantine equations. And there are many other examples, and you will learn more about these in later lectures. So that's all for me. I hope you've enjoyed this, and I will be open to hearing from you. If you want to write to me, contact me, you can certainly find me online. For now, bye-bye.